Log on, tune in, find out. Another good idea from Cambridge.
Okay, thanks very much. So the first thing I want to say that the thing that I'm going to talk about tonight is a collaboration with Stephen Harris from Edinburgh and Andrew Stewart from Warwick. Okay. So does this work?
I didn't plug in anything.
So now it's work. Okay, can I use that longest tape?
Yeah, just stick it straight there.
Okay, good. Right. So this is the summary of what I want to say. So I am interested in inverse problems in which the unknown is a whole function. So I think I am happy with this one. Okay. So I am interested in the case that what we are searching for is a function. So, and I'm going to use the Bayesian formulation. But since, as a result of the fact that my unknown is a function, I'm interested in a measure in the space of functions. So I spent some time explaining how we can make sense of the Bayes rule in that case. And then I am also interested in the cases that a Bessov measure, which I'm going to explain in a few minutes what I mean by that, works better as a prior measure. And then I'm going to show you some well-posedness results when we have Bessov measure as the prior measure. Now, this infinite dimensional setting, one of the useful things about it, we think, is that we can then quantify accurately the approximations of the posterior on finite dimensional spaces. So that is the next thing that I'm going to tell you about. And then finally, I will give an example of the application of all these in the case of an inverse elliptic problem. Okay, so this is the problem that I'm concerned with. So I want to find the function u from this operator equation. So G is the operator between Banach spaces x and y. Eta is some y-valued random variable, and I know the statistical properties of eta. And then what I'm interested in is finding an estimate of this function u. Right, so as an example, this of course can happen in the context of inverse partial differential equations. For example, if you have such an elliptic equation and what you are searching for, and this kind of thing, for example, comes up in geophysical application. So you can look at this as the pressure, and the pressure of the flow, underground flow, is what you can measure, and what you are searching for is the permeability of the rock. So therefore, these are your measurements, the measurements of pressure at some finite k points, and then you want to find the whole function u. Now P is just a solution of this elliptic partial differential equation as a forward problem. So your operator G is just some functional of the solution operator of your PDE. So the properties of it you know very well, because at an elliptic PDE you have the estimates for it from PDE theory. So in that sense, when I'm talking about the fact that G is given, I'm I mean something like that. Right, so inverse problems are usually ill-posed, and that is the case that we are interested in. That's why we need to use regularization. So basically we need to inject some prior information, because as it is, it's ill-posed. So you need to change it somehow, and you change it by injecting some prior information, which is basically the same thing as saying that we're going to regularize it. So just briefly, the classical regularization, because then I'm going to kind of comment on it when I'm explaining the Bayesian one. So I have an inverse problem which is ill-posed. So first thing I do, in case the existence is the problem, I weaken my expectation of a solution, and then, assuming that I know some prior information about U, for example, I know it lives in some certain function space subset of X, then I try to regularize it in the sense that I want now the solution that I am getting, I want it to be stable with respect to small changes in Y, so that's why I add a regularization term. And stability is very important, because at the end of the day we're going to approximate and we need a stability. So what we are doing, the original problem, we are going to changing it to this problem by adding this component to the problem, some appropriate prior information. And what we are hoping is obtaining some reasonable approximation. So now note that what we are getting from this is just a single function, which is the argument of this function over here. Very well. Now in the Bayesian regularization, what we are interested in, as you heard in the last 4 talks about it a lot, what we are interested in is the whole distribution of U over this function space X. And then we are interested in this probability distribution, as Peter Jan said, for different reasons. For example, we want to have some information about local maximizer of this probability, or you want to find the kind of relative probabilities of or different local maximizers. So you are interested in that, and then what you are given again is just some measurements, either a function or some vector. But then you know more about the error in your problem. You know the statistical properties of this error, and then you are confident enough to build up a distribution based on your prior belief on your function space. So now you kind of you know a prior to solving your problem, you know more, but then you are expecting to get more as well. You want to have the whole distribution. So what you want to get is this kind of updated distribution, which we call posterior. So we have this one, we have some data, we combine this, and we hope to get something better, which we call posterior. Now this is based on Bayes' rule. So what you saw in all the last talks were this, that probability of U given Y equals or is proportional to probability of U, the prior probability, times the likelihood. Now the problem here is that we are on the infinite dimensional space, so we don't have any density with respect to Lebesgue measure, so I cannot write it like that. So the only natural way of thinking about it is thinking about Bayes' rule as giving the Radon-Nikodym derivative of the posterior with respect to prior, because both of them are now living in on the same function space. And then this is just proportional to the likelihood, so it comes from the Bayes' rule. But then you need to make sense of it. Right, so again, there also we are changing the original ill-posed problem to this one, which we are hoping to be well posed, and that is what I'm concerned with in this talk. I'm going to find the conditions on G and mu naught so that the posterior that I get is well posed. Now, So I have written it, this is just a notation. So this is the likelihood is a positive function is less than 1 if your y is finite dimensional. So therefore, just as a notation, I can write it as the exponential of minus some function phi, u and y. So for example, in that case, so this depends on the type of the distribution that you have for your noise. So if you have the Gaussian, then obviously that is just e to the power of minus half Gaussian with covariance gamma y minus gu squared weighted by gamma. Now, okay, so as I said, I'm concerned with this, with the well-posedness of mu y. So just looking at this, so this was my phi. This is minus phi. So just looking at it, if I write it as, so let me write it again, using the normalizing constant, because I want to have a probability measure e to the power of minus phi. And obviously that z, you heard about it again in the previous talks. Can you see this? Right. So what you expect, I mean, just looking at this, what you expect are the following. First of all, you want phi to be measurable with respect to u, with respect to mu naught. Then, of course, you want your zy to be finite, because otherwise you will not be able to get a well-defined probability measure. And you also want it to be away from 0, again, because you want a well-defined probability measure. So you see, so I want conditions on phi, but it depends on the type of mu naught that I choose, because these are the type of condition that I need on it. So let me start by introducing what type of the prior I would like to choose. Now I'm interested in best of priors. So they are priors, that they are measures that are constructed based on wavelet expansions, and therefore they are appropriate for the cases that you have that your unknown function is a function with some local discontinuities, and also they promote a sparsity. So for example, if you think about that example that we started with, the inverse elliptic one, I said that it refers to finding rock permeability in some geophysical problems. Now in those applications you can easily have different kind of materials in the rock next to each other. So you have a function which is continuous almost everywhere, but at some sets of measure 0 you have discontinuity. And you know that such a function is sparse in wavelet expansions, because you know the members of a wavelet basis are very localized. So such functions are much more sparse, say, compared to when you use Fourier expansion. So therefore there are applications that we are interested in using wavelet basis for our unknown. And that is important because when you have the sparse expansion in a specific basis and you have chosen your prior such that it respects that, then you will have less trouble approximating, numerical approximating. You can have quicker approximations. Now how these are defined? They are defined through Caronin-Loew expansions of their draws. So basically this is just a generalization of the KL expansion for the Gaussian case. So these were introduced by Lassa, Saxman, and Siltanen in 2009, and how they work is the following. So if I remind you about the KL expansion for the Gaussian case, so if you have a measure, Gaussian measure with covariance operator C on a functional space X, and if you know that C has the eigensystem lambda j psi j, then you know that any draw from that measure can be written as an expansion in that basis, in basis psi j, but an expansion which has random coefficients, obviously, and psi j are just a standard Gaussian distribution in each direction. So in each direction psi j you have a standard Gaussian distribution weighted like root lambda j, and lambda j and psi j, as I said, are the eigenbasis of C. Now, so what they did, Lassas and et al., well, of course, you don't have a covariance operator in the case of best of measures, but they kind of generalized this idea. They said, let's consider psi j like this thing, exponential of minus a half x to the q for any q, and q can be anything bigger than or equal 1. So they generalize it from exponent 2 to q. Psi j now can be wavelet basis, and then they choose lambda j in an appropriate way. So why they choose lambda j in this form, I'll just mention it quickly. So I just remind you that the best of space BSQ with this particular exponent are defined as this space. The functions in LQ such that the components of U in the basis psi j is weighted like this. So you have this sum finite. Now, again, going back to the Gaussian, formally you can say, just formally, because you know that you don't have any density, that you can say the density of that, just formally, is equal to e to the power of minus a half the norm of U in the Cameron-Martinez space of that to the power of 2. And the Cameron-Martinez space is just the image of C to the power of half. So this is something constructed by C, but then what they said, they say, let's choose lambda j so that you get a best of a space like that acting something similar to the Cameron-Martinez space. And for that reason, if I put it just shortly, for that reason they are choosing lambda j as that thing. You can see that it's related to the way that the best of spaces is introduced. So now this is how a best of measure is defined. So mu naught is a BSQQ best of measure if draws U from mu naught satisfy this random series, as I explained before. Kappa is just a constant that we have added to this series because we need it for some practical reason, but it's not that important, so you can ignore it for now. Now, so if you forget about all these technicalities, what matters is this. You can show, just using the norm and the definition of the norm and the best of space, that such a measure, the measure that I just defined, charges the best of space with this exponent with probability 1, with t less than s minus d over q. Again, if you are not familiar with the best of space, you can forget it in a moment, because it turns out that they charge the Hölder continuous functions with probability 1 as well. Now, why I'm telling all this? Because what I'm interested in, especially for this one, I want to know what kind of functions are integrable with respect to mu naught. So I want to find the bound on mu naught integrable functions. So from Gaussian theory, you know that you have Fernic theorem, which says that e to the power of alpha ux squared is bounded if mu naught of x equals 1. So this is what I said over there, the upper bound for mu naught integrable functions. So Lassas and et al., the ones who have introduced the measures, they have shown that these kind of functions are integrable with respect to mu naught. But as I said, we know that the Hölder continuous functions are also have measure 1 also under mu naught. So what about them? Or if you want to compare it with the Gaussian case, what about any function x for which you have mu naught of x equal 1? Can you say something like this? Because that is the case that is given to us by Fernic theorem for the Gaussian case, which relies very much on the Gaussianity anyway. And it turns out that, again, for the familiar Hölder spaces, we couldn't go up to any space x, but for the Hölder continuous function, that helps a lot. And that is very helpful for us. For example, consider that Log permeability case, because the Hölder continuous functions can be quite useful for that case. So now you can find the conditions on phi, because now you have a bound on the mu naught integrable functions. So just a quick point that the fact that you have wavelet basis is very much useful in finding that bound on that integral, because in wavelet basis, the CT normal view is written in this nice way, because wavelet basis, they are conditional basis for Hölder continuous functions. Right, now that we have the properties of mu naught, then we can say what kind of conditions on phi I need, because that is what I'm searching for. I want conditions on phi, I want condition on mu naught to give me the well-posedness of the posterior. So these are the conditions. So the first box is just telling you that you want appropriate upper and lower bound on phi. You want the Lipschitz continuity in u, and you want the Lipschitz continuity in y. Now you can see the effect of the theorem that I just showed you with the Fernic-like theorem for the best of measures here. You want these coefficients to be integrable. So now having those, then you have the well-posedness. If your phi satisfies potential conditions, and then if you have a best of or Gaussian measure with mu naught of x, because the best of measures, they are generalization of Gaussian, so they include that case as well. Then you have a well-defined mu y, so the Radon-Nikodym derivative makes sense. And then you have also well-posedness. The small changes in data results in a small changes in measures, but then how you measure the small changes in measures, you need to put a metric on the space of measures, and we are putting the Hellinger metric, because the Hellinger metric gives a nice way of bounding the expectations on their different measures. So now, as I said, the well-posedness, one of the reasons this is important is because then you can quantify the approximations of the posterior measure. So therefore, if you have a finite dimensional approximation of your posterior, then you know where you are standing compared to that true posterior, the well-posed posterior that we have. So that is the next thing. So let's say you have a PDE, you have some approximation of its solution, and therefore it is showing itself in the form of phi, because if you just look at it, I told you that G, for example, if you have an inverse PDE, is related to the solution operator of the PDE. So therefore, and this is the phi was just the definition. So phi is just related to the forward operator of the forward solution operator of the PDE. So if you discretize it, it shows itself here in phi. So let's say you have discretized it and you want to use the same Radon-Nikodym derivatives that you have used before. Now, again, first of all, you need to make sure that the Radon-Nikodym derivatives make sense. So mu and mu n, they exist. So you want the same kind of condition that I told you in the well-definedness part. Then, if you know that phi n is approximating phi nice enough in this sense, again note that I have the Fernic-like result appearing here, then you have that the approximated measure also is converging to mu with the same speed psi of n. So basically, the approximation properties of the forward problem is translating to the approximation properties of the solution of the inverse problem. Now, if for the finite dimensional approximation and the weak error that might be of interest, remember we started with the wavelet basis because we thought it might be better for the type of the unknown function that we want to find. So if you have chosen a good basis, so for example you have the large permeability problem, you have chosen the wavelet basis, so it makes sense that actually consider a discretization of your unknown function in your PD also in the same wavelet basis. So the same basis that you made your prior measure using it, you are using it to discretize the original PDE because you chose it at the first place with that in mind. If you do that, then it turns out that that part of the posterior which lives on the span of those n eigenfunctions you have discretized using them satisfies such equation with respect to the part of the prior which lives on the same space. Now you have a finite dimensional posterior measure. Of course, I cannot compare it directly to the original posterior measure which lives on another space, but I can talk about the expectations of functions under these measures, which is so-called weak error for the uncertainty quantification people. And then again, under reasonable conditions that I don't want to bother you with, you can show that you have the convergence of the weak error. So I wanted to go back to the elliptic case and show that if you choose your x to be the space of Hölder continuous function for any t positive, phi satisfies potential conditions, the conditions that we need for the well-definedness of the posterior. Then you choose your prior in a way that charges Hölder continuous function with probability 1. So you choose the exponent, the relevant exponent appropriately, then you get well-definedness. And then it turns out that the weak error for n-dimensional posterior is of order n to the power of minus t over d as well. And that's all I wanted to say. Thanks very much.
Okay. Any questions?
You mentioned an application in the beginning about the geophysical application where you measure pressure under a solid, under a rock. Could you say something more about this?
Yes, so what, right. So you have the flow of water in the rock, and by Darcy's law, you know that if this is the permeability, e to the u is the permeability, you know that the velocity of the water is permeability times gradient of pressure. Then, assuming incompressibility for the water, you have divergence of V 0. Therefore, you get divergence of e to the power of u gradient t equals 0. So this was the elliptic PD that I started with. Now, the thing that you can measure, so apparently it's easy to drill a hole and measure the, it's not that difficult compared to measuring the permeability directly. To drill a hole and measure the pressure of the water. So these are your measurements, and what you want to find is the permeability.
Sometimes in practice it's possible to measure the permeability at the boundary. Can you add that to your model?
Yes. Yes. So for example, well, we have a very, of course it would get very much more complicated, but so you construct your space X to be the CT functions with let's say u equals 0 on D, on the boundary of your domain, and then you try to build up your prior in a way that respects that.
Okay, I think we should end here. This is the last talk. So thank all the speakers again.